Lesson 21, tossing up and down. Number 1, how long will it take an object to fall 6 meters? So the 6 meters is the height of the fall. And we want to know how long, which is going to be to find the t. So what equation relates time to height? T is equal to the square root of h all over 4.9. The h, we put in the 6. And then I go to a calculator in order to figure that out. 6 divided by 4.9 equals 1.22. So I take the square root of 1.22, and it's 1.1. Number 2, an object falls for 3.9 seconds. How far does it fall? So here we have a time. We want to know how far it falls. In other words, we're looking for the h, the height of the fall. So we're still going to use the time to drop equation. It's just that we're going to solve for the h instead of the t. So on the left-hand side, we have 3.9. And on the right-hand side, we have the h. To get the h by itself, the first thing we do is to square both sides. That's a little bit messy here. Let's erase some of this other stuff that we don't really need so we can focus better. Okay, so we squared both sides. And 3.9 squared, got to figure that out. 3.9 times 3.9, 15.21. On the right-hand side, the square and the square root cancel out, so we only have h all over 4.9. We now multiply both sides by 4.9. We get 74.5. .5 meters. Number 3. What does it mean that the acceleration of gravity is negative 9.8 meters per second squared? For every second, velocity changes by negative 9.8. Number 4, convert 12.1 grams to kilograms. Well, I know that there are 1,000 grams in 1 kilogram. So how do I change 1,000 to be 1? Well, the decimal point is originally there. To change 1,000 to 1, I move the decimal point over 1, 2, 3 places. So I'm going to take this 12.1 and I'm going to move the decimal point over 3 places in the same direction, left, and I'm going to get 0.0121 kilograms. Number 5, can science discuss the wisdom of building a certain type of machine? No. Science cannot talk about whether or not a decision to build something is the right or wrong decision. Number 6, Can science debate the physical consequences of building a certain kind of machine? Yes, it can. It can say, if you build this machine, then it's going to produce this much pollution, it's going to use this much energy, it's going to create this much heat, it's going to move this fast, etc., etc. But it cannot say whether or not that is a wise decision. Number 7, use the long equation to derive an equation with V1 by itself on the left-hand side. So we want to get the VI by itself. The first thing I'm going to do is subtract off x sub I from both sides. And then I'm going to subtract off the 1/2 AT squared from both sides. And now I'm going to divide both sides by t. And then I'll be almost done. The t's on the right-hand side are going to cancel, leaving the VI by itself. I'm going to rewrite the final answer flip-flop so that the VI is on the left-hand side instead of on the right. And there we have our answer. Number 8. What are the independent variables of an experiment? These are the qualities the researcher chooses. So for instance, let's say that the researcher is trying to figure out how much water or how water affects the growth of a plant. And so the researcher decides to keep data on how much water the person puts into the soil, how often and how much, and then measures the height of the plant. So the researcher might choose to water it every single day, 3 millimeters or 3 milliliters or 7 milliliters, or measure out every week and put in a gallon of water. But the researcher decides how much water is going to be put in. The resulting growth is also measured, but the researcher doesn't decide to let the plant grow 1 inch or 5 inches or 2 centimeters. The researcher only decides on their own how much water. And so it's the amount of water or the timing of the water that is the independent variables. The amount of growth results from that, and so the growth is the dependent variable. Number 9, a red herring is when a debater tries to distract the other person away from the topic at hand by saying something very emotional. Please spend the next 27 seconds reading the main ideas, the purpose, relevance, success, the grades in the next quiz. Number 1, a ball is tossed up with a velocity of 29.4 meters per second. It lands 6 seconds later. Find the velocity at each second. During this time, the acceleration is negative 9.8 meters per second squared. So the velocity changes by that number each second. It's going to start off, as we said, positive 29.4. Positive meaning it's going upwards. During the next second, that velocity is going to change by a negative 9.8. And so we get positive 19.6 as our velocity after 1 second. During the next second, it changes by negative 9.8 again. Positive 19.6 minus 9.8 is a positive 9.8. During the next second, it changes by negative 9.8 again. Positive 9.8 minus 9.8 is 0. During the next second, it changes its velocity by negative 9.8. 0 minus 9.8 is negative 9.8. So you see what's happening here? It starts off with a very big positive number that's very fast going upwards. And gradually, it gets a little bit smaller and smaller, but you're still in the positive direction. So it's getting slower and slower, but still going up. Then it's stationary for an instant. That's the tippy top. And then it starts coming down. So we see that it has a negative sign, meaning that it's down. And we start off with a relatively small number, and it's going to get bigger and bigger in the negative direction, meaning faster and faster downwards. Okay, so during the next second, it changes by, again, negative 9.8. We get negative 19.6. At the end of another second, it's now going negative 29.4. Okay, so notice something else about this situation. Number 2, the velocity at the bottom is always the same number, same digits, but the opposite sign of the launch. So in our example here, we started off with positive 29.4. We ended up with negative 29.4. The same digits of 2, 9, and 4, but the opposite sign, showing that it's going down at the end, which makes sense. The velocity at the midpoint is always 0. Now, that does not mean that it's hovering there for a moment. It's not like the cartoons where the coyote is floating in the middle of the air before he starts to fall. It is only for an instant, not a length of time. It's kind of hard to understand, but remember in geometry class, I taught geometry at Grant years and years ago, and I believe it was the very first math lesson. We are taught what a point is. And here I have a dot that I just put on the screen. And we would say in geometry class that a point is represented by a dot on a piece of paper, but that dot has a length and a width and a height or whatever, has dimensions. There's a certain amount of ink there, and I could measure the width of it, and I could measure the height of it. I could try to make it smaller and smaller, but it's still going to have a width and a height. I could have a single molecule of ink on there, and even that single molecule is going to have a width and a height. A geometric point does not have a length or a height. It is an imaginary concept with no size whatsoever, just a location. And in reality, that doesn't really happen. It's more of an imaginary philosophical kind of a thing, but yet that's the case. Okay, so when I say that the velocity is 0 at the tippy top of the trajectory, it is not for 1 millisecond that it's 0. It's not for a microsecond or a nanosecond or a picosecond, a trillionth of a second, a quadrillionth of a second. It's just for an instant. No space, just one moment of time. It's kind of hard to understand, I guess, but that's the way that it works. Number 4, note that the acceleration is always, okay, let's see here. Acceleration of a tossed object gives lots of students problems. Since gravity does not change during the flight, the acceleration due to gravity does not change. It is a common mistake to think that the sign of the acceleration changes when the object changes from moving up to moving down. That is a mistake. Don't think that. The sign does not change. Next paragraph. Remember that the direction of gravity is always pulling down in the negative direction. So the acceleration is always negative, no matter if it's moving up or if it's moving down. At the very tippy top of the trajectory, the velocity is 0, but not the acceleration. Gravity is still working, so the acceleration is still negative 9.8.